Okay, everyone, welcome back to the first lecture for the week 2 material. So in the first part of the lecture, we saw basically how to use panel data without individual heterogeneity. So we did not really exploit the power of panel data. And then only towards the end of the first week material, we actually started putting in individual fixed effects. And by that means, we actually started using the true power of panel data. Now, in this week, we will actually deepen our knowledge a little bit on these fixed effects methods. Then we will talk about so-called random effects models. And finally, then we talk a lot about clustering, like about estimating standard errors for fixed effects models. And finally, look at dynamic models. Okay, so let's jump right into the material. So the first part is a little bit of recap what we did. So as you remember, we did panel data without individual heterogeneity, and then we used pretty much the same ideas even when the model contains some fixed effects. So what we've learned is that we can simply apply the same idea GMM after applying a certain transformation. So for instance, first differencing or the within transformation. In today's tutorial, we also saw that in some special cases, they are actually absolutely the same. So when t is 2, they're exactly the same. Yeah, but in general, they have a couple of differences and they depend on the properties of the model error term. Namely, one tends to perform slightly better when than the other when the model error is a random walk. I think the first difference estimator is a little bit better then. And otherwise, when there is, the model error is serially uncorrelated, then the fixed effects estimator should be a little bit better. Okay, now what was the cost of deriving these estimators under, the presence of unobserved individual heterogeneity? Well, we had to strengthen the assumption that we had too strict exogeneity. Yeah, so before contemporaneous uncorrelatedness was enough, but now that we kind of mix up all the time periods by using these transformations, we have to use something stronger, namely strict exogeneity. Okay, so now the first thing that I want to remark on is basically notation. So what we have used is that we went to the IT level and we have used the within transformation there. Now, you can also write this in matrix form, and this is what is introduced in many books. I think also Wooldridge uses this kind of notation. Where first you look at the model 1, which is, well, the same model that we had before in stacked form. And it looks pretty much similar to what we had before. The only difference here is now that the alpha is multiplied with this JT, which is simply a vector of ones. Yeah, the rest is pretty standard as before. And now, how can you get the within transformed data from this stacked version? Well, you can employ the time demeaning matrix. This is called here QT, and this is the definition from Wooldridge. So you have here the identity matrix with T dimensions, and then you have here, sorry, the second prime here is of course wrong. So on the first one it's correct, the second one is wrong. I will correct that. Yeah, so you have here these combinations of these vectors of 1, and it turns out that this here in the brackets is simply 1 over t, and then JT is a matrix that has 1 in every component. Okay, now this QT has some nice properties. So for instance, it's symmetric and it has this property here, idempotent. And that means that if you multiply this matrix with itself, it comes out pretty much itself again at the end. Yeah, so that's like the property here. And it has a rank of t minus 1. Okay, now this matrix then can simply be used by, well, in order to get the within transformed data. So you take this matrix and you pre-multiply. So you multiply everything from the left here, this QT on the left-hand side and on the right-hand side. So each of these summands on the right-hand side gets multiplied by QT. And it turns out that, well, you can actually easily check that. That this then yields again the within transformed data. Right, so kind of here when you look at this matrix JT, which has kind of rows of ones, and you multiply this with another matrix. That means like this row of ones is simply you sum up the row of the matrix that you multiply it with. So for instance, this xi matrix, and then you divide it by 1/t. Yeah? So this means that you really take the averages. Okay. Good. So this is about the matrix notation. Then there's something that you also often see. So that's called the least squares dummy variables, which basically means that you can also derive the fixed effects estimator simply by putting in individual dummies into your regression. Yeah. So this is the whole point of this exercise here. So this alpha I can be written as simply n individual specific dummy variables. Yeah. So like each of, for instance, D1 is a dummy that stands for individual 1, and Dn stands for individual capital N, right? So, and you see that, of course, for each I, only one of those individual dummy variables will be 1. Okay, now if you look at this, and you remember from previous courses the dummy variable trap, it should be clear that there should be no constant regressor in this model, because if there was a constant regressor, it would be collinear with the sum of all these individual dummy variables. Yeah? So, okay. Now, this is pretty much similar to what we had before. So if you compare this to a previous data transformation, for instance, first differencing or the within transformation, they also wipe out any time invariant variables. Yeah. So for instance, the constant regressor would also be kicked out of the model. Yeah. So because if you do not wipe them out, if you keep the constant regressor in the model, that means after the transformation, all the constants are turned into zeros. And this matrix here will be like of reduced rank and therefore not invertible. Now, yeah, so if you simply use OLS and you put individual dummies into your regression, it can be shown that this least squares dummy variables estimator is numerically exactly the same as the fixed effects estimator. However, typically nowadays you would prefer the fixed effects estimator because these dummy variables, of course, they increase the dimension of the vector of observed covariates, and therefore computing the LSDV is numerically more costly as compared to the fixed effects estimator if you have many individuals, which is typically the case in microeconomic panels. Now, of course, you could also do something different, and this is actually what Stata does. So all you have to kind of avoid is that like these individual dummies or like the fixed effects are collinear with, for instance, an intercept. So Stata actually sometimes reports an intercept even if you have fixed effects in the model. And that may be surprising to you because, well, one standard way of, using fixed effect models is to normalize the intercept to 0. We assume this is not there simply, right? Now, Stata wants to keep the intercept in the model, and therefore it has to use a different normalization, and it uses this one here. It assumes that the alpha i's, the individual effects, sum to 0 over the whole sample. And using that transformation, Stata claims that now you can interpret the intercept that Stata reports as the effect, as the average effect of the alpha. Yep. Okay, so then some more general comments on the whole fixed effects business. Now, when we include fixed effects, that like graphically simply means that for each individual, we allow the least squares regression line to have a different cutoff. Yeah? So the line has the same slope, but we allow for different cutoffs for each individuals. However, sometimes you would also like to do something similar for the time. Yeah? So you would like to account for time effects, which can, for instance, be regarded as macroeconomic shocks that have an effect on all individuals and affect each individual in the same way. Yeah? So those are simply shocks that appear in a particular period. All the individuals are affected in the same way. Yeah, but of course, so that means they would not get an I index, but they get a T index because they only happen in particular points in time. Yeah, so this is what is written in this model here. So you see the alpha I does not change across time. That's the individual effect. And here this lambda T, this does not change across individuals. And that's the time specific effect. Okay, so now this is actually also a very popular model. So this is also called a two-way error components model because, well, we have like the model error, the unobserved part of the model has an idiosyncratic error, and then on top of that, it has two parts, namely an individual specific and a time specific effect. Now, in principle, we can use the same ideas as we used for the fixed effects estimator. You know, if you remember for the fixed effect, this within transformation simply used the idea that, well, the alpha I doesn't change across time. Therefore, if we reduce the time average from each observation, so from each observation IT, that means the alpha I will drop out. Well, I mean, something similar could work across individuals, right? So we know that these lambda t's, they don't change across individuals, and therefore we could take each IT observations minus the individual average. Yeah? So, and therefore also the lambda t's will drop out. Now, of course, if you do this, it's actually a little bit more complicated computationally because you're kind of removing averages twice. So in the end, you will have to add the overall average again. Yeah, but we don't go into this at this point. What you do in practice is actually that you simply put some time-specific dummies in your regression. Yeah, so because our panel data is simply short, we can do this. We can just put some time dummies in our regression. And then we typically assume that these dummies are uncorrelated with the model error. So we can simply rewrite the model with this x tilde notation. And this x tilde notation contains the original x, and it also contains the time dummies. Yeah, so and what you kind of the advantage of this is that now you can also, well, account for these macroeconomic shocks, which is in some applications pretty important. So graphically, you can allow for individual and time-specific intercepts. Okay. Now, back to time invariant regressors. So we saw that one of the main disadvantages of this within transformation or the first differencing is that you cannot identify the effects of time invariant observed characteristics. So the classic would be a gender dummy, for instance, because those don't change over time. And therefore, once you do the within transformation, they get wiped out together with the alpha. Okay, so that's bad. Yeah, so one way to deal with this, as we will see right after this, is to use a random effects approach. Yeah? So we make some more stronger assumptions, or we use a little trick, namely that we interact these time invariant observed characteristics with time dummies. Yeah, so this would be the original model. I assumed here for simplicity that we only have 2 time periods. And the WI here is a variable that is observed. Yeah, that is kind of the difference to alpha I. But similar to alpha I, it's also time invariant. And the x's, those are variables that are nice. They vary across both I and t, yeah, so individuals and time. Now, if you look at this model, it's pretty clear that alpha and WI, they're perfectly collinear. So you actually cannot separate, you cannot identify the gamma here because, well, whatever the effect of gamma is, you could simply redefine alpha, yeah, and, you know, capture, basically create a new fixed effect, alpha I star, that captures the effect of WI. So again, that's one of these instances where different values for the parameters are plausible for generating your data. And therefore, we cannot, well, we don't have identification, and therefore estimation does not make sense. Now, as an alternative, as we mentioned before, we can try interacting this WI variable with a time dummy. So here I interacted with the second period, and let's see what that does. So if you, so keep that model here in mind, the WI is interacted with DI2. Okay, now let's say we have strict exogeneity, everything is perfectly fine, everything is as we would like it to have. And we look at the first time period for the group where the dummy variable is 1. Yeah, so we assume that WI here is, for simplicity, is simply a dummy variable, for instance, gender. Yeah, so let's say WI is female. So you look at the condition expectation of the outcome variable for all females. And this is what you get. Because you are in the first time period, okay. Yeah, actually, sorry, this should be an I index still. Yeah, so there's no alpha 1 here. Yeah? But the important part is that this dummy variable in the first time period will be 0. So you see that the gamma does not appear here, and also, of course, the W. So here we have that, well, we are in the second time period, and now the WI gamma appears. And actually, because you set W here to 1, you can actually, you could in principle plug this in here, right? So this is simply 1. And therefore, if you take the second equation minus the first equation, you get this here. Huh? Okay, so far, so good. The alpha has been removed. Now you could do the same thing in the base group. So in the group where the W is actually 0. So that would be, we do the same exercise for the males. And now again, there is no gamma because, well, this dummy is now always 0. So you see that here there's no gamma. So if we take the difference between the second equation and the first equation, I have to fix here these indices. Of course, this has to be a 2, yeah, but I will fix that on the version that you will see online. We get something that looks pretty familiar. So we get this part and this part. This is, of course, the same. And therefore, well, I mean, the idea is that we simply compare this, like this last line, this difference between the time periods to this difference between the time periods, yeah, where, of course, the only change from here to there is that here we look at the females, so where the dummy variable is 1, and here we look at the males. Yeah, okay. Where the dummy variable is 0. Okay, so if you simply take the difference, then you see that this is again gamma. Yeah, you can also, of course, like this is kind of take the difference over time in the first group minus the difference over time in the second group. We can also write the same thing by, you know, taking the difference in time between the groups minus the difference in time like between the groups again. Yeah, so here difference in period 2, here difference in period 1. Yeah, so compare this with the first expression, and thus we can actually interpret gamma as the change in the difference between the group 1, like for instance here the females and the males, from period 1 to period 2. Yeah, so we cannot, for instance, identify the gender pay gap, which would be, which would, for instance, refer to this here. Yeah? So this would be the effect, for instance, of gender. If this is wages, yeah? So this would be our idea of the gender pay gap. That we cannot identify because gender is time constant. However, we can actually still identify changes in the gender pay gap if we interact this dummy variable with time dummies. Yeah? And that is kind of like what I wanted to show you here. So not all is lost. Of course, you lose something, but yeah, there's still stuff you can do when you have time invariant observed characteristics. Okay, so that's the first part. The next part continues with the random effects model.